It's okay?
Okay.
Okay, it's okay.
All right. So I want to start by thanking the organizers for switching this to remote on such short notice because of my flight was canceled due to weather. And the other thing I want to say is I'd hope to do this in person, but I'm currently recruiting new graduate students. So if you like this talk, or if you're interested in the other things that I'm working on, feel free to look me up and send me an email. So let's start with an overview of what the contribution of this research was. So it's an ordinal library, and we implemented it in Agda, and it's for Brouwer tree style ordinal. So what that means is you've got a zero, you've got a successor, and then if you've got a function that produces ordinals, you can take the limit of that function. And those limits can be over an arbitrary type. So normally a Brouwer tree just you have a sequence indexed by natural numbers, but for more flexibility with proving termination, we let you do a function with any type as the domain, and possibly empty type. And the key properties that this library has is it has a well-founded strict ordering. And so that well-founded ordering means that we can do recursion. We can use this as the thing that's decreasing to prove that something's terminating. And it also has a well-behaved maximum operator. And it's got two key properties that we really kind of struggled to get to work together, which is that it respects that well-founded ordering. If all of the things you're taking the maximum of are strictly smaller, then their maximum will be strictly smaller as well. And it also is actually the least upper bound. So it interacts well with the limits of sequences, and it has all the properties you'd want from a maximum. And we're able to do this without any strong axioms. This is pretty much just bare type theory. So we don't use univalence, we don't use quotient types, we don't use function extensionality, and we certainly don't use excluded middle, which is what makes all of this hard. In kind of classical math, it's easy to get all of these properties, but doing it in a way that works constructively was where the challenge of this research was. So now I'm going to kind of zoom out and talk about what is the problem we're trying to solve, why do we care about this, and what we actually did to solve it. So in dependently typed languages, usually you want to have all of your functions terminate, and this has some kind of important implications in terms of consistency, because it means that you can't accidentally write a proof of false that works by running forever. And it's also important to establish decidable type checking of your language, because when you have terms in your types, you have to normalize those terms to compare your types, and if your functions don't terminate, that can take forever. And so usually the way that this is checked is by ensuring that any recursive calls you make are structurally decreasing. They're on a direct subterm of some inductive type that you pattern matched on in your function. So for example, if you're writing the successor case of plus, you could say, well, it's the successor of m and 1 less than m, and that doesn't work well because it's not structurally smaller than n. Whereas the way to do it structurally decreasing would be to pattern match on n and then to directly take that field that was in that constructor. But this doesn't always work, and there are some functions that you just can't express this way. So if we look at our kind of classic example of a dependently typed quicksort, so sorting the empty list is empty, and sorting a list with a head and a tail, you take everything that's less than the head, and you put it before the head after you sort it, and then you take everything that's greater than the head, and you put it after the head once you've sorted it. And so we've got this recursive call on the result of calling filter. So this isn't something that is structurally smaller than the list we started with. It's smaller, but it's not structurally smaller. And so we need some way to be able to express that this is actually getting smaller, that this is actually going to terminate, even if it doesn't follow this kind of naive structural relation. And so that's where well-founded recursion comes in. So basically, there's you can write a type that's parameterized over some relation, and if that relation is well-founded, which is basically the constructive version of saying it has no infinite descending chains, then you get this function that lets you do recursion with it. It says if you take an argument and you have a recursor that says I can call that on any argument, any other argument, as long as it's strictly smaller, then you can produce something of your result type for that argument, and then you can close over that and basically run this recursively on any argument that you give it. And so the key here is you're explicitly saying what's decreasing because you've parameterized over this well-founded, strictly less than relation. So for our quicksort, what this would look like is now you take this extra argument of self, which is basically the function we're going to call recursively. And then every time you have a recursive call, you provide a proof that strictly less than relation actually holds. And then you can use this WFREC combinator to close over the whole thing and get something that's equivalent to the directly recursive way of writing the function. And so for quicksort, the proof that you would need is about the properties of filter, and so we're not going to get into that. But it basically takes it from something that the type checker is checking directly and internalizes it into the language, into something that the programmer can provide as a proof in the dependently typed language. And under the hood, this works by structural recursion on this proof of well-foundedness, but that's opaque to the programmer. They don't need to see how that's working. So that works great, and for natural numbers, you can just use the normal less than operation is well-founded, and you can use that. But in dependently typed languages, sometimes we have higher order structures, and sometimes numbers aren't enough for the kinds of highly dependent things that we'd want to do with dependent types. So the running example I'm going to work with is universes, universes a la Tarski. If you're familiar with what that is. And so basically you have a type of codes, and this is a data structure that is describing a type. And then you have an interpretation function that says, if you give me a code, I can actually compute the type of things represented by that code. And the usual way you'd write this is with induction recursion. And so you've got... and that's not true. That's kind of, this is separate from the contribution, but it's the motivating example that led to this line of research. So, for example, you could have a constructor that says, well, we've got a code that represents the top type if we've got some sort of like subtyping lattice, and we could say here's a code for natural numbers. And then when we get to a code for dependent function types, this is where things get interesting, because you say, so a function type has its domain and its codomain. So you take a code for its domain, but because it's a dependent function type, the codomain is parameterized by an element of the domain. So this is where that kind of mutual dependency between the definition of the codes and the elements of comes in. And you could add more constructors depending on what kinds of type you're trying to express. And so the interesting question comes, what if we want to write something that is recursive on these codes that's decreasing, but decreasing in something that's more subtle than the naive structural way? So basically, what if we wanted to assign a size to our codes? And the tricky case is, how do we assign a size to these dependent function types? Because we want the whole pi type to be bigger than the maximum of all of the domain. So we want it to be bigger than all of the codes in the domain. We want it to be bigger than all of the codes in the codomain. But to do that, it needs to be bigger than the codomain for every possible index. And there's possibly infinitely many elements of the domain that are indexing this codomain. So we're not going to have any luck assigning a number to this to give it a size. And so this is where ordinals come in, and they can do this kind of transfinite recursion, and they can assign sizes to things that are infinitely big but still strictly ordered. So the classic Brouwer tree type, which is one of many ways of expressing ordinals, is basically it's kind of an infinitary tree. And so you've got 0, which is a leaf, and then you've got a successor operator, which says if you've got any Brouwer ordinal, you can take something that is 1 strictly larger than that. And then the key thing is we have this limit constructor that says if you have a sequence of ordinals, and the way we represent a sequence is by a function that produces ordinals, then we can take the limit of that sequence and say, here's something that is as big as everything in that sequence. And so this is a very kind of lightweight representation of ordinals. It's fairly easy to construct things that have the properties we want. And so, for example, you can represent the kind of smallest infinite ordinal as the limit of the identity function, right? Basically, the limit of all of these, the limit of all of the kind of natural number ordinals. I think actually identity might be the wrong function there. I apologize for that. But this is limited because it only works for sequences that are indexed by natural numbers. And so if we want something that can assign sizes to, for example, our representation of the syntax of dependent types that we saw earlier, we need something more general, where instead our limits are parameterized over any type. And so the way that we're going to express any type is we're going to assume that we have some kind of code representing types and that it's parameterized over an element of that code. And so this is really useful for, obviously, for proving termination of things involving these, if you've defined your own universe or if you've defined your own code types, because now you can take any function that's indexed by the type type in your code, in your universe, and you can take the least upper bound, all of it. And because we're doing a universalitarski, it has the same level as whatever your code type has. So if your code is a small type at like universe level 0, then your ordinals will also be at universe level 0, and then you can get increasingly larger and larger ordinals as you increase the universe level of your code type. Now, the reason we are interested in these is because we want to use them to prove that things are terminating. And so to do this, we need a strictly less than ordering on our trees. And so we'll build that from the less than ordering. And so this is going to have some of the properties you'd expect. 0 is less than everything. And the successor is monotone. So if x is less than y, successor of s is less than successor of y. And then the key property of the limit is that for any argument, the limit of f is as big as f of x. And it's, more importantly, it is the smallest ordinal with such a property. So it's effectively, it's the least upper bound of the range of the function that you give it. And so this ordering is well-founded if you define strictly less than to be the successor is less than. And this lets you do a form of transfinite recursion where you've got possibly infinite structures, but you're still showing that they can only descend finitely deep, kind of infinite width, but finite depth. But because we're working in a constructive system, we haven't assumed excluded middle or choice or anything like that. We don't have this kind of trichotomy lemma that says that any two ordinals are either less or greater than or equal. You can't prove that, and that's basically the hurdle that we're trying to work around with our contribution. So as an example of where we would want, so this is great, but this only works for things with one argument. So we started off with structural recursion, then we had natural numbers, now we've got higher order structures, and the last piece to kind of have the maximum flexibility in proving that things terminate is we want to be able to prove that things terminate in multiple arguments. And the way we're going to do multiple arguments is taking the maximum of a bunch of ordinals. So you can take a bunch of ordinals and compress them into a single ordinal. And so the motivating example for this, and this is quite literally the motivating example in the sense that it's the problem I got stuck in during my doctoral work that led to this whole line of research, is when you're trying to take the intersection of two different types. So say we've got codes and we want to say, I want to take the information that's in both of those codes and combine them together. And then to do that, this is kind of going to be defined mutually with a way of saying, well, if I've got two codes, I want a way to convert between one or the other. And this is assuming we've got some sort of like error code that can say that this cast failed, that these two things aren't actually comparable. And so these are mutually defined. If this smelled like gradual types to you, if you're familiar with that, that's exactly where it comes from. But this could also have applications if you're doing kind of coercions between types and general types, or independent types, or if you were defining something with subtyping, or if you were doing an explicitly well-typed unification algorithm. They're all kind of the same problem where you've got two types and you're traversing them in parallel and combining their information in some way. And so the trickiness comes from the dependency of when we're doing these pi types. So if you're saying you want to take the intersection of two pi types. To take the intersection of the domains, that's easy. You just take the intersection of the domains. But the tricky part is that then to take the intersection of the codomains, your result type is going to be indexed over this DOM12, the intersection of the domains, but your inputs are instead indexed over this. The first one's indexed over DOM1, and the second one's indexed over DOM2. And so to get something that has the right type, you end up having to take. You can just take the intersection of those two codomains, but the arguments that you pass them, you have to cast them to the right type. You have to basically run them through some explicit conversion. And so now if our meet and our cast are mutually defined, the tricky part is proving that this is actually terminating and that this is getting smaller. And so it feels like it should be. And the way that you can show this is you can say, well, what's actually getting smaller is the maximum of the size of the two codes we're casting between, or the two codes we're taking the intersection of. But to show that this is actually smaller, we need this property, which is literally just the sizes of the things in the recursive calls to cast, which is that the maximum of the maximum of our inputs is going to be strictly bigger than the maximum of basically the size of the already intersected domains and each of the domains we're doing the recursive call. Now, if our maximum is well behaved like a normal maximum, then this is easy to show, right? Because the maximum is idempotent, maximum of DOM1 and DOM1 should be DOM1, and the maximum should be commutative. It shouldn't matter what order, and it should be associative. We should be able to rearrange all of these things and prove this. So we should be able to do this, but you can't actually do this. The Brouwer trees as we presented them, it's very tricky to have a maximum that actually has these properties. So more generally, what we really want from our maximum operator to do this kind of recursion is we want to be able to do well-founded recursion on multiple arguments and do that by taking the maximum of their sizes. And we want it to be strictly monotone. So what that means is if you're decreasing in each argument, then the maximum of those should also be strictly decreasing. And we want it to be well behaved so that we can do the kind of algebraic equational rearrangements that we saw earlier, right? So it should be associative, it should be commutative, it should be the actual least upper bound, which is going to mean that it's monotone and it's idempotent and it has all of those nice mathematical properties that let us actually rearrange these inequalities and prove the basic properties that we would expect out of it. So here's how not to do that. But through these two attempts, we're going to come to our actual solution. So the kind of naive way of doing it is to do it using a limit. So you say, okay, we want the maximum of two things. Let's just take a sequence that had two elements and take the limit of that. And this is, in fact, the least upper bound because our limit was, by definition, the least upper bound. But this isn't strictly monotone, and that's what's really tricky, is we need to prove basically that the successor commutes over limits, and that doesn't hold. And so we can't do that constructively. And so instead, you can say, okay, well, let's just do something recursively on our definition. So we could say the maximum of 0 with anything is that thing. The maximum of two successors is the successor of the maximum, and the maximum with the limit is the limit of the maximum. And if you do this, this is great. This is strictly monotone, but this isn't the least upper bound because it's not actually idempotent with our ordering. We need the limit of basically taking the max of these two limits to be less than the limit itself. And you can't do that because of the way the limits distribute over. You end up having to take the limit over two separate arguments, and there's no way to kind of combine those. And this also is tricky because it requires all of our limits to be non-empty to get even basic properties like monotonicity. So finally, at the very end of my talk that I'm running a little over time on, here's how you actually, the actual solution to the problem. And so it turns out the solution was hiding in Kleina's fixed point theorem. So what we do is for any term, we can take this kind of infinity max, which is taking that inductive maximum definition and maxing it with itself an infinite number of times. And the way you can do this an infinite number of times is with limits. And so this is the Kleina fixed point, which is basically the solution to the max of t and x is equal to x. And so these things are idempotent. You can max them with themselves. And, well, what's infinity plus 1 is the same as infinity when we're not talking about ordinals. And so that's great. We now have a kind of subset of our trees that have this property. I'm going to kind of skip over this. There were some tricks we did to get non-empty limits. But what we actually do to take all of these pieces and tie them together is we define a new type of ordinals. And this is the subset of our Brouwer trees that fulfill this idempotence property. That say that when you take the max of a tree with itself, it's less than the initial thing you started with. And this infinity max lets us compute limits that have this property. So if we want to take the limit of these strictly monotone Brouwer trees, we do that by, under the hood, the kind of raw tree that's underneath, we max it with itself an infinite number of times. And then we get something that has an opaque interface with these kind of smart constructors that look exactly like the constructors we had for original. So we've got a strictly monotone version of 0, a strictly monotone version of successor, and a strictly monotone version of the limit that has that works under the hood by taking this kind of infinite max with itself. And we can, because we've got all of these same constructors, we can convert any tree to a strictly monotone Brouwer tree, and it preserves the ordering. So we get all of the properties we wanted, but now this maximum is actually has all of those properties we want from the maximum. So effectively what we did is there were some limits that were ill-behaved, and we carved those out, and we got rid of all the bad trees, and now we still have enough trees left over that satisfy the properties we need. So I'm going to skip through this discussion, and I'm going to wrap it up there. So thank you. Thank you for listening.
Thanks for the talk. And again, as usual, if you have any questions, please use this mic and say your name and affiliation. Thank you.
Hi, it's Mevin Menon-Bertrand for the University of Cambridge, and I think I saw it very fast on your last slide, playing with this kind of like a size-based induction in Coq when you start having like kind of big inductive types and so on can become very, very tedious. Because you have a lot of these goals and like, oh, max of all these things is smaller than this other stuff. And Coq is great because we have the LIA tactic that just solves all these goals in one liner, and you can just like do an all LIA that prunes all of these in just a very simple way. And so I was wondering whether you had thought about having the same kind of support for automation with your Brouwer trees. It seems like it would be doable because you have all the nice algebraic properties, but yeah.
Absolutely. That's basically kind of the next step of this research is because we get this nice equational system where you can reason about things. First off, it lets you turn the kind of inequalities into equations. You can treat this kind of semi-lattice you can look at as an idempotent commutative monoid. And so by doing that, you can use kind of tactic-based things. It would also be well suited to like Frex or other kind of more algebraic-based rewriting systems. But yeah, absolutely, that's one advantage of doing this. And if you don't have a well-behaved maximum operator. So yeah, that's definitely kind of the next thing I'm going to look at in terms of doing this.
Thank you.
Any...
Hi, René Thiemann from University of Innsbruck. I wondered, you now considered a data structure with this Brouwer trees which has exactly 1 0, 1 successor, 1 limit. Would this be extendable, your work, that you have, say, several different successors or different limits, or is it not possible?
So that's interesting. I hadn't considered that, and I'll be honest. It's mostly just because I didn't need it for the particular thing I was trying to prove was terminating. I think it could be possible if you had different successors in the kind of underlying inductive type. That then, in theory, if you were to lift that to the strictly monotone version where you carve away these kind of ill-behaved limits, my intuition tells me that all of those properties should still work. So if you had multiple successors you wanted to kind of fork off in different directions, I think that should work fine. But that's pure conjecture at this point. So yeah, I know that these aren't necessarily the most mathematically well-behaved. So for example, there's some weird properties because you've got the well-behaved maximum. You've got like the maximum of 0 and 0 is equivalent to the limit of any sequence that produces all zeros, which means you've got 0 is equivalent to a limit. So you lose this property that everything is either is exactly one of 0 or successor or limit. Things can be built with different constructors but still be equivalent in our ordering. So that might end up causing problems, and that's something I kind of didn't look at because it's a nice mathematical property that I didn't need for the thing I was trying to prove terminating. But yeah, I think multiple successors would work, but I very well could be proved wrong.
Okay, thank you.
I have time for one more quick questions. Yes.
Hi, Ruben Rowe, Royal Holloway, University of London. You said there was something on your last slide, and it said you could convert any tree to one of these strictly monotone Brouwer trees, and then you've also been saying various points talking about carving out and discarding like the bad limits. I may be missing something here, but is this there seems to be some mismatch there between what you're saying. I'm just trying to understand what's going on there. You sort of had this. You seem to be saying that you could.
Right. That's fair. So basically, we can. It's not. So there's a function. Technically speaking, there's a homomorphism between normal Brouwer trees and the strictly monotone ones, and it's. But the not every Brouwer tree is the underlying raw tree. So like the strictly monotone Brouwer trees were a subset of normal Brouwer trees. And not every Brouwer tree will be represented in that subset, but you can take any Brouwer tree and lift it to a strictly monotone Brouwer tree that has the same ordering properties with the liftings of other Brouwer trees. So what it says is, yeah, if we have some limit that's ill-behaved, that doesn't end up in our strictly monotone version. But we can pass it through this function that will produce a different limit, but when we pass all of our trees through that function, we get back the same ordering properties that we wanted from the original limit. So basically, and I'm not sure, I don't want to say something wrong in terms of like the actual like size of these types, but basically it lets you. Kind of the way to think of it is the problem with the normal Brouwer trees was that they didn't have all of the ordering properties that we wanted with respect to the maximum. And so when we're lifting them, we might end up kind of collapsing to the subset where things get lifted to equivalent trees, but they're getting lifted to equivalent trees that by this collision is exactly what we want, because the collision gives us these ordering properties of the maximum that we didn't have before.
That's helpful. Thank you very much. Thank you.
Okay, thank you.
All right. Let's thank the speaker again.
Thank you.
So